So the question says write down system representation equation for an example system with 3 inputs, 4 states and 2 outputs. Now we know that system representation, state space representation is x dot is equal to ax plus bu, y is equal to cx plus du. Now looking at the question that's in front of us, we see that we need to have the system with 3 inputs, which means we have u1, u2, u3, 4 states x1, x2, x3, x4, and then we have 2 outputs, which means we have y1, y2. Now we can start then to write our differential equation, state differential equation in state space. It therefore means we'll have x1, x2, 3, 4, all of that dot being equal to x1, x2, x3, x4 plus u1, u2, u3. Now, that being the case, if we look at the sizes of the matrices, it can help us to write an example of a system. You see that the output here, the size of this is 4 by 1. And the size here is also 4 by 1. Now, the matrix here, this matrix, this A matrix, this one, it's a matrix that's generated by multiplying a certain matrix of size m by n to give us, it multiplies m by n, it multiplies this m by n matrix with this 4 by 1 matrix to give us another 4 by 1 matrix. So from our matrix calculation rules, it means therefore, in order for these things to be, these two matrices, that and that, to be able to be multiplied, we need this n to be the same as this value. Right? We need that to be the result, to be the same. So which means we already know then that this is supposed to be, we know that this is supposed to be 4 as well. Now, given that we want to establish a result whereby we have a result which is 4 by 1, we know that the number of the result will have the same, will have the following size. The result, it will have m by 1, just by virtue of multiplying these two matrices. We know that the result will have m by 1. The m will be from that, the 1 will be from the second one. But we need this m by 1 to be 4 by 1. This means, therefore, we can conclude that this value here is 4. So that means here we can fill in a random system of 4 by 4. That could be our A matrix as a random example. It's a random example, but it's a valid random example because we know that the matrix here has to be of size 4 by 4. And we can follow this similar logic here, whereby we have a 3, we have a matrix that's 3 by 1, and we need to multiply this matrix as 3 by 1 with a certain number, with a certain matrix which is m by n, and that should give us a 4 by 1 result, because we are adding it to a 4 by 1. So we need a result whereby we multiply. So in order for us to multiply, we know that this has to be equal to that. So automatically we remove this. We write 3. We know that's going to be 3. But the result here the result of the two multiplications is going to be m by 1. But for this calculation to make sense, so that we can add this to equal that, it means this has to be the same as that. So it means this result has to be 4 by 1. Now that means that here already we know by default that has to be 4. So that's how now we know the size of the matrix B. It has to be 4 by 3. So we can then write a random system B here with 4 columns, 1, 2, 3, 4 columns with 3 rows, 2, 3. So this would be a random B matrix. Now we can apply the same logic. We should apply the same logic to obtain your output equation. So the output equation is going to be y1, y2 is equal to some matrix x1, x2, x3, x4, plus, that's the C matrix, plus the D matrix, and you have u1, u2, u3. Now, what we need to establish here is that we have a 2 by 1 result, we have a 4 by 1. So we need this 4 by 1 multiplied by something here, m by n. 4 by 1 times m by n has to be equal to 2 by 1. So right from the onset, this has to be equal, so we know that this has to be 4. And the result has to be m by 1. So the m has to be 2. Cancel that, we put a 2 here. So this has to be a 2 by 4 in order for this multiplication to make sense. So we'll have 2. That could be one example of a random system that we give. We follow the similar logic here. We have a 3 by 1, which has to be multiplying something here by 3, because this has to make sense. But this number has to be equal to that 2, so it has to be a 2 by 3. Therefore, we can make that random matrix, which will have 2 rows, 3 columns. Now this would then be, if I were to cancel that, this would then be a random example of a system with 3 inputs, 4 states, and 2 outputs. So the idea here is just to try and be able to follow the logic to make sure that you are able to know the rules of multiplication of matrices and the rules of addition of matrices. Question 14 says consider systems with output y and input u of t described by the following differential equations. Derive state variable representation for each. Now in this case, then let's try and first tackle question A. So as a general rule, when you tackle such problems, what you will notice is that if the differential equation is of the first order, so the order of it has a single state. So the order of the differential equation generally gives you the number of states that your module will have. So in this case, if you have a single differential equation describing a system, the order of the differential equation gives you the number of states. So in this case, we have a first order. So which means we'll have only one state here. And then we have a second order differential equation because here is the highest derivative, the second derivative. So we'll have two states. And here we have the third order differential equation. We have three states. So that's the general rule. The first general rule is the order of the differential equation gives you the number of states if you want to convert. The second general rule to make these things easy is that you assign your states, your output variable, you assign it to a state and its derivatives. So that's how you can easily get your states. You can do it the other way, but the most straightforward way of doing it is to have each state being described by the output or its derivatives. Now let's solve question A. So question A to get is the first order differential equation. So there is one state, and that state is x. So we say we let x equals to y. This becomes our state. Now then the differential equation, the state differential equation can be rewritten now. You can rewrite the state differential equation as 10 dx dt is equal to u minus x. Remember, our state differential equations have to be of the form x dot is equal to ax plus bu, y is equal to cx plus du. This means that we have here dx dt, or rather, let me put it this way, or rather x dot being equal to minus 1 over 10 x plus 1 over 10 u. That's the state differential equation. So this is the state differential equation. Now we need an output equation. So our output equation becomes from the definition. So the definition says y is equal to x and nothing to do with the d, or we can simply write it as 0u. So then this becomes our state variable representation of this single input, single state, right? So we can therefore say a is equal to minus 1 over 10, b is equal to 1 over 10, c is equal to 1, d is equal to 0. So 14b, we are supposed to consider this system, and we need to write that differential equation as a state variable. So in 14b, we say ordinary differential equation is of second order. Therefore, there are two states. So we let x1 be equal to y. We let x1 be equal to y and x2 be equal to y dot. So the derivatives and the output y, we assign them to the states. So which means now therefore the ODE becomes 10 dx2 dx2 dt. Remember, the first derivative is the first derivative is the second state. It therefore means that the second derivative is the derivative of y dot, which means it's in actual fact x2 dot. Let me just clarify that first. Let me just clarify that by showing you this example. So here we say dy dt squared. It's the same as saying dt times. So this is the same. Now what we are saying is this part we have already declared it as x2. So which means we have, that's how you write it, right? Because we have already said dy dt is equal to x2. Okay, so going back, we can say therefore say the ODE becomes 10 dy 2x1 plus x2 is equal to u. Now, this implies that we have the x2 dt being equal to u minus x2 minus 2x1 all over 10. Right? So we can write now for our two-state, we can write the state differential equation. And remember, the way we write the state differential equation is by x is equal to ax plus bu. So in this case, we can write the first derivative x1 dot is equal to x1 dot is equal to, remember x1 is y. Remember x1 is equal to y. So x1 dot is equal to y dot. But y dot is equal to x2. So it's equal to x2. Alright, and x2 dot is equal to minus 1 over 5 x1, that is from here, minus 1 over 10 x2 plus 1 over 10 u. This implies that now we can write x1 x2 dot being equal to, you can write it in matrix form this way. X1 doesn't have x1 dot doesn't have anything to do with x1, so this will be 0, this will be 1. So x1 dot will be equal to 0 times x1 plus 1 times x2, which is what we are having here. X2 dot is this equation is going to be minus 1 over 5 minus 1 over 10. And x2 dot is also related to u in this sense, whereas x1 dot is not related. So now we have just established our matrix A, and our matrix B. Now we need to write the output equation. So the output equation, the output is 1, y is equal to, so the output equation is y is equal to cx plus du. So by definition, y is simply equal to x1. So x1 times x2, or maybe let me write it this way first, so that it becomes easier. Let me just squeeze it here. So output equation at cx plus du. So we know that y is equal to x1, which is equal to x1 plus 0x2 plus 0u. Therefore, we can write y is equal to x1, x2 plus u. So it's not related to u, and it's related only to x1. And therefore, we have just written now our output equation and our state equation. So the two give us the state variable representation. We are back with question 15. Question 15 says, consider systems with output y of t and input u of t defined by the transfer functions below, this transfer function and that. And the question is, derive the state variable representation for each. Now, with the transfer function here to the state variable representation, what we need to note is the order of the transfer function here would also dictate how many states your equation would have. So what we're saying here, because this is a second order system, it's a second order transfer function because here we have s to the power 2 for the poles. It means we'll have two states. Here, because we have third order, we will have three states. So now let us proceed to answer the question A. Let's start with question A. In fact, let's just do question A. Question B will just be obvious from our workings with question A. So for question A, the transfer function by definition. So our approach is to take it back to the differential equation first, because we know how to work out a differential equation. It's going to be the output y of s over the input u of s. And this is equal to 2 alpha s squared plus beta. Now this implies that we have alpha s squared plus beta times y of s is equal to 2u of s. We take the inverse Laplace transform. We then have alpha, second derivative of y, dt plus beta y is equal to 2u of t. Right, now for our two states, because we already know that there has to be two states, the equation here, we will let y be equal to x1 and x2 be equal to y dot. So now from here on we can then take the differential equation becomes alpha alpha times the derivative of x2 and derivative of t of x2 plus beta times y, which is x1, is equal to 2u. By the way, you can exchange this. You can assign x1 to y dot, x2 to y. It doesn't matter, as long as, because it will produce an equivalent representation, but not exactly the same representation. So it doesn't matter anyway. It will be an equivalent representation with this similar system behavior for analysis purposes and control purposes. So now, if this is the case, then we can I can make dx2 subject to the formula, and then I can get minus beta over alpha x1 plus 2 over alpha u. Now we are ready to write the state equation. State differential equation, which is x dot is equal to ax plus bu. So we can write x1 dot is equal to what? x1 is equal to y, is equal to y dot. This effectively is the same as saying x2. x2 dot is given by the equation above, by this equation above, and that gives us minus beta over alpha x1 plus 2 over alpha u. In fact, we can even rewrite it this way. We can also say plus 0 times x2 plus 2 over alpha u, which means here we can also say this is like 0. This is the same as saying 0 times x1 plus 0 times x2, 1 times x2 plus 0 times u. So that is your x1. So then we can rewrite this as x1, x2 dot, which is equal to x1, x2 plus u. So we have the first x1 dot being equal to 0 times x1, 1 times x2, and 0 times u. x2 dot is equal to negative beta over alpha times x1, 0 times x2, and 2 over alpha times u. So here we have just got our state differential equation. The next one is the output equation. The output equation is equal to y is equal to cx plus, okay, sorry, write it on top so that you can see clearly, is equal to y is equal to cx plus du. Now, by definition, y is equal to x1. That's what we said here, which implies that y is equal to x1 plus 0 times x2 plus 0 times u. So we can write then the state equation this way. This is going to be 0, 1, 0. And then, therefore, here we have our output equation. This is your output equation. We can even use Octave to show that the transfer function is equal to 2s plus 8 over s squared plus 4s plus 3 by inserting the A matrix, B matrix, C matrix, and the D matrix as simply equals to 0 into Octave. Remember, Octave, in order for Octave to work, you always have to load the control system package. But you can even verify your calculation using